Hi physics students, this is the second video for the topic 4.2 traveling waves, and in this video I'm going to reiterate some of the basic ideas of waves in terms of defining terms. As well, I'm going to talk about the wave equation, which you've already been using, and I'm going to end this video by talking about sound waves, which is a very important part of your IB physics curriculum. Okay, so just to review some of the basic ideas behind waves, you should be very comfortable with all of these ideas at this point. Remember that the amplitude of a wave refers to basically how deep a trough is or how high a crest is as measured from the wave's equilibrium position. Okay. Keep in mind that equilibrium position might not always be zero. Okay, we've seen a couple of situations in class where that might be the case. Okay, the wavelength, which of course is the horizontal length of one cycle of the wave, and the wavelength, as you recall, is the horizontal distance between either crests or troughs as measured on a displacement position graph, not a displacement time graph. Okay, if you measure the same corresponding distance on a displacement time graph, that is the horizontal distance between two crests or troughs, that's the time taken for one complete oscillation, which of course is called the period. And you know that the period and the frequency are related as inverses of one another. Okay, so the period, the units of period, capital T, are seconds. The units of frequency, which is 1 over T, are 1 over seconds or hertz. So again, you should be very comfortable with all of these concepts at this point in the class. Okay. Again, the displacement is the change in distance. Displacement implies a vector, and indeed this is a vector, which is why we have positive and negative on the y-axis. Okay. Intensity, something that you should be aware of. This is maybe something new for you. What it refers to is simply the power per unit area that is received through a wave. Okay, so intensity is power over area. And it turns out that intensity is proportional to the amplitude squared. You don't have to be able to derive this, but you should be aware that I is proportional to A squared. That's important. Okay. Now, again, the wave speed, that's just the speed at which the wave fronts pass a fixed point. Okay, and the IB wants you to be able to derive the wave equation. It's a very easy derivation. In fact, it's so conceptually straightforward that there's hardly even a derivation at all, and I'll give you one way to think about it. Okay, so if you think about a train with freight cars having a particular velocity, in this particular case going in the positive direction or to the right. Okay, and if you stand right here, say at this point right here, and you you have your stopwatch and you measure the amount of time it takes for this entire freight car to pass you. That is, you start the timer right here, and when the back of the car gets to that same position, you stop the timer. Well, if you think about each of these cars as a wave, then the physical distance of this freight car would be the wavelength, and the amount of time it took for you to measure between the front of the car and the end of the car would be the period. Okay, so in that case, the speed of the car would be given by the length of the car and the amount of time it took for the entire car to pass you. Going back over to this equation right here, okay, the length of the car would be the wavelength, of course, and the amount of time it took to pass you was the period. So for any wave, this is called the wave equation. For any wave, V is equal to the wavelength, lambda, over the period. You more often see it written as V equals F lambda. That's the version that we'll end up using, especially when we deal with light. Light is a wave where V is actually C, which is 3 times 10 to the 8 meters per second. Okay, so that's kind of the derivation of the wave equation. You can do it in lots of different ways. I really like the analogy to a train and a freight car because it really makes sort of physical sense to me. But however you want to perceive it, it's still distance over time, which is the speed. Okay. All right, let's try an example. Go ahead and pause the video and try this one. Okay, so you're being given a wave. The x and y units are centimeters, so this is a displacement distance graph. What's the wave's wavelength? That's pretty easy. You just measure the distance between two repeating points, okay, either crest to crest or trough to trough. In this case, I found it easy to do from this equilibrium position to this equilibrium position. That's 4 centimeters, okay. And again, however you choose to do it, however you choose to measure the wavelength is up to you. The wave's amplitude, if you just read the graph, it's 3 centimeters. And of course, these, you can measure any peak or any trough, they're going to be the same. If this wave is moving at a speed of 10 centimeters per second, what's its frequency? Okay, so we know V, we know lambda because we just measured it. frequency, you just rearrange the wave equation and you get 2.5 hertz. And then they ask you on the graph, sketch a wave having half this amplitude and twice the wavelength. Pretty straightforward, right? So again, the amplitude here would be 1.5 and twice the wavelength. Okay, so the original wave, you see it's traced out one complete wave here, right? For every one complete wave, you have only half a purple wave. You see that? Okay, so pretty straightforward. All right, now try this one. I think you've seen this one before maybe. The distance between points A and B on water waves is 5 meters. What's the wavelength? Well, you should be able to analyze this diagram and answer that question. Note that there are 2.5 complete wavelengths over the course of this 5-meter distance, okay? All right. That being the case, you can do some pretty simple math and figure out that the wavelength is 2 meters, all right? And one thing you could do if this were on paper is you could get a ruler and actually measure it, right? If 5 waves pass by point B every 15 seconds, what's the frequency? Frequency, again, is number of waves per unit time. That's 5 over 15, which is 1/3 of a hertz. What's the period? It's 1 over that, so it's 3. And the speed, of course, using the wave equation, we have more than enough information than we need to actually solve this problem. And I got 0.67 meters per second. Okay, another example. Radio wave. Radio waves are electromagnetic waves, and they move at the speed of light because they are light of a different frequency, a frequency with which human eyes cannot detect or cannot see. Okay, so if it has a frequency of 99.5 megahertz, okay, and that's in the FM radio. That's in the FM radio range, okay? So if you have your favorite radio station, let's say it's 99.5 FM, what that means is that that radio station broadcasts their music and their voices and everything else at a frequency of 99.5 million hertz, okay? We'll talk more about that later when we talk about electromagnetic waves. But what's its wavelength? Well, all we do is we deal with the wave equation again, noting that V is actually C, which is 3 times 10 to the 8 meters per second. And it turns out that radio waves, FM radio waves, are on the order of a couple of meters long. Pretty cool, okay? Here's another example about water waves. Go ahead and read it first. Okay, so water waves we treat as a transverse wave, even though they're a little more complicated. I'll talk about that in the next video. These water waves in this example travel 4.4 meters in 1.8 seconds. They give you the period. Seems like you have enough information. In fact, you do. The speed of the waves would be 2.4 meters per second. Notice how I'm using sort of the 5-step problem-solving method here. I'm writing down clearly what I'm given, what I'm not given, the equation, put the numbers in with units, and then the final answer is right there, okay? And then the wavelength, again, use the wave equation as I got 2.9 meters for that. Okay, I'm going to talk a little bit about sound waves, and we're going to be doing some stuff with sound waves in the lab. This is fun stuff. Now, sound is a kind of wave that you're equally familiar with, hopefully, throughout your life. Maybe equally familiar with sound as you are with water, although maybe you never really thought about sound as being a wave. Turns out sound is a longitudinal wave, and what it is it's a series of compressions, what we call compressions and rarefactions of air molecules. Okay, we're going to start simple and talk about sound through air because that's what you're hearing right now. Okay, so really what it is, okay, technically, is it's a series of successive high-low air pressure zones. And again, the high pressure are called compressions because the actual air molecules are being compressed. They're closer together in a certain volume, number per unit volume, and low would be a rarefaction. Energy is transferred through the molecules of the medium in periodic fashion, okay? So everything that we've learned about waves so far with the wave equation, et cetera, applies to sound as well, even though it's a longitudinal wave and not the more familiar transverse wave. Okay? All right, so you can see if this is a closed chamber with a piston, right? If you displace this piston, in other words, if you apply a force to it when it does work on the molecules, what it's going to do is it's going to create a series of high pressure and relatively low pressure regions, okay? And that's going to travel through the medium at a certain particular speed, all right? Now, we can represent sound waves and longitudinal waves as transverse waves. And don't get confused about this. It's not as confusing as it might seem. This particular video right here shows the relative displacement and pressure of air molecules in this chamber, which is meant to represent this chamber over here, you might want to pause the video and study these displacement and pressure graphs very closely to make sure that you understand what's being displayed here, okay? Okay, it turns out that the speed of sound waves depends on the property of the medium through which they're traveling. And of course, this is true of any sort of wave, okay? Remember when we talked about springs and we talked about tighter and looser springs and lighter and heavier springs, okay? The lighter the spring or the tighter the spring, the greater the wave speed through it, okay? It turns out that hot air carries sound significantly more quickly than cold air, okay? And if you think about what sound is going through air, it's the vibration, the periodic vibration of molecules. In hot air, the molecules are already moving faster to begin with, so it kind of makes sense, at least to me, that if the molecules are moving faster to begin with, then energy would pass through them more quickly than if they're kind of lumbering around and moving really slowly to begin with, okay? And in fact, you can actually sense the difference between hot air and cold air between summer and winter in places that have extreme temperature differences. So here's a table from your Cutnell and Johnson physics text showing the speed of sounds in solids, liquids, and gases. And one of the things you notice immediately is that the speed of sound is much higher in solids than it is in gases, okay? And that's because in solids, the molecules are much closer together and they're held in sort of a rigid sort of lattice structure. So energy is able to go through them more efficiently and more quickly than they are through gases where the molecules are much, much farther apart in comparison, okay? All right, and it turns out that the speed of sound is proportional to the pressure and inversely proportional to the density, the square root of. Now, you don't have to derive this. I'm just telling you this because it's kind of an interesting thing. But if you look at, we're going to do some work with the speed of sound through air. If you look at the difference between the speed of sound, say at 0 degrees and say 100 degrees Celsius, it's considerably different, right? We're talking over 40 degrees, over 40 meters per second, all right? So kind of interesting stuff, okay? All right, now it turns out that we can quantify the frequency of sound waves audibly, and that is because the higher the frequency, the higher we hear the pitch. It's kind of interesting, and again, we'll play with this in class, and maybe we'll bring in some musical instruments. So pitch is something that's like it's a psychological reaction or physiological reaction of our ears to frequencies of sound. What we hear is the higher the frequency or the more sound waves that are coming into our eardrums per unit time, the higher the pitch, okay? So if you look at some of these are from Logger Pro, from the Vernier microphones, okay? Sound pressure against time, you should be able to look at these two graphs and tell me what the frequency would be. Obviously, the frequency of the bottom one is higher than the frequency of the top one. Go ahead and give it a try, okay? I show that the frequency here is about 256 hertz, and on the bottom, it's about double that, okay? So make sure that you can look at this actual real data and ascertain these two values for these relative frequencies, okay? Okay, so we'll do a couple of examples. Determine the difference between the speed of sound through air on a hot summer's day and a cold winter's day. Okay, I gave you that equation before, which I didn't actually talk that much about. But the equation is the speed is 331 plus 0.6 TC. Okay, so it's 0.6 degrees Celsius for every degree temperature difference. Okay, all right. Okay, and a cold winter's day, right? So you see, it's a significant difference. It's 32 meters per second difference between summer and winter. Okay, here's a classic one. How far away is a storm? If you note, it's a 7-second delay between the lightning flash and the sound of the thunder. You have to assume an outside air temperature of 27 degrees Celsius, and I got that it's about 2.43 kilometers away. Okay, last example, the past paper question from an IB exam. Okay. One method of finding the position of a fish beneath a boat is to send out a pulse of sound waves from the bottom of the boat and time how long the pulse takes to return is shown below. Okay, so they're giving you the speed of sound in water. It's 1,500 meters per second. And they're saying the time between the pulse leaving the emitter and returning to the receiver is 10 milliseconds. Calculate the distance from the bottom of the boat to the fish. This is a very easy problem if you can read the question a couple of times and understand what they're asking for. Okay. I got that the distance is 7.5 meters, okay? So remember, you have to actually consider the fact that the pulse goes down, hits the fish, and comes back up.